Hi, today I want to make a hopefully quick video about how we can use concentration inequalities to bound the generalization error. So before we continue with bounding the generalization error, let me explain what is actually the generalization error, and for that we will need a little bit of statistical learning theory. Specifically, we want to formulate our learning problem, and we do it as follows. So I assume that we have some data, the standard setting, and specifically I assume that the data comes from some data generating distribution D, which in principle is unknown to us. Then we assume that there is some mapping, so something that maps our x into our y, and we assume that this mapping comes from some function class head of f. And then finally, we also need to assume, or we need to choose a certain loss function, something that measures how good is our model f from this function class head of f performing. So how close is f of x to the true labels y. So once we have that, what we are in essence interested in is to compute the risk of our problem. And the risk is defined as follows. So we say that we have these data points x, y, which are sampled from our data generating distribution D. And then we want to compute the risk corresponding to a certain mapping or function f from our function class head of f for our chosen loss function. So then the risk is given by the expected value over all the possible distributions of x and y, of the loss of our model f on x and y. So essentially this is measuring how good is our choice of function, the f that we chose from our function class, performing for predicting y when we are measuring the performance using our loss function L in expected value over all possible data generated from D. Statistical learning theory, or learning in general, then seeks to find some f in our function class head of f that minimizes this what we call population risk. So it's this arg min of the R of f. What's the problem with this formulation? As I said, we don't actually have access to the true data generating distribution. And typically what we have is we only have access to samples from this data generating distribution. So we usually assume I have some data, some xi, yi, and capital N samples of this, which I assume are IID samples from my data generating distribution. So what I can do is I can only compute my risk using these samples. So I can only compute what we call the empirical risk, which is defined as follows. It's this 1 over n of the sum of the loss functions between our prediction on xi and the true label yi. And then we come to the approximation that we finally make, is that we then approximate our optimal function choice by minimizing this empirical risk as opposed to the true risk that we initially had. And the generalization error that we're then interested in analyzing is this gap between the true risk, so this expected value over samples from our data generating distribution, and the empirical risk, so the empirical average of our losses computed over our samples that we have from the data set. So in my setting, this is what I refer to as the generalization error, but you might be familiar with a slightly different setting of the generalization error, which is as follows. So in practice, we don't know the true data generating distribution D, which was the problem that we were discussing before. So how we can approximate the generalization error is by essentially considering a second sample of data. So some, in this notation, x hat, y hat, we assume we have capital M of those samples. And we use this kind of test or validation sample to approximate the generalization error. So instead of computing the distance between the true risk and the empirical risk, I'm now computing the distance between the empirical risk over one batch of data and the empirical risk over a second batch of data. All right, so this was the setup. So we have formulated what we mean with the generalization error. And now we want to move on to actually understanding this generalization error and specifically understanding the distance between the expected value of our loss and this empirical average computed over samples of our data. So in order to do this, we will be using concentration inequalities. So let's briefly look into what are concentration inequalities. So in their most general form, they give some kind of probability bound for a random variable to be concentrated around its mean, or for it to essentially deviate from its mean or from some other value. So for example, it could be something like this, where we say, what's the probability that our random variable x deviates an amount a from the expected value of x itself? And ideally, we want to bound this by some other constant, in this case, b. So how exactly can we use this? How does this kind of formulation relate to what we were saying before, in that we are interested in bounding the true risk deviation from the empirical risk? What we would then say is that suppose our x denotes the empirical risk, then basically the expected value of x would be the true risk, since the expected value of the empirical risk amounts back to just the true risk itself. So this already shows how we can, if we manage to find a concentration inequality of this form, how we can then somehow bound the deviation of x being the empirical risk, around the expected value of x, which amounts to the true risk. Okay, so let's start with a kind of simple example of a concentration inequality, which will bring us to Markov's inequality. So suppose that we have drinks that are sold on campus of some university, and we denote the number of calories in that drink by some random variable x, and we say that the range of this random variable x is between 0 and 110. Now suppose that I tell you that the average of the number of calories, so the expected value of x, is 50. And then the question is, what can we say about the fraction of drinks that have more than 100 calories? Is there any way we can bound how many drinks, or the fraction of drinks that have more than 100 calories? The answer is yes, and the answer is we can bound it by 1/2. And why is this the case? Well, suppose that we are in a setting where more than 1/2 of the drinks sold on campus have more than 110 calories, then already the average would exceed 50. So even if you consider the very extreme example that slightly more than 1/2 of the drinks have 100 calories and slightly less than 1/2 have 0, already that would mean that my average is going to be more than 50. And this is essentially a example of Markov's inequality. So Markov's inequality states the following: suppose we have some non-negative. It's important that it's non-negative, because if we can go negative, we cannot use this bound. But if x is a non-negative variable, and if we set some epsilon greater than 0, then basically we can say that the probability that x exceeds epsilon is bounded by the expected value of x divided by epsilon itself. So how does this relate to the previous example that we had? If I told you that the expected value of x is 50, and we chose epsilon to be 100 calories, then essentially indeed 50 divided by 100 would be 1/2, which is what we had before. We can generalize Markov's inequality into something a little bit more complicated, which is Chebyshev's inequality. So in particular, we would like to bound the fluctuation of a random variable around its mean. So remember Markov's inequality that I have here at the top in green. And now consider that I choose some random variable which is x minus mu squared, where mu is the expected value of x. This variable is non-negative, so we can directly apply Markov's inequality to obtain the following. So I can obtain the fact that the probability of x minus mu squared being greater than some epsilon squared, it would be bounded by the expected value of that random variable divided by epsilon squared, directly from Markov's inequality. And then we can use two things. So the first thing we can use is that this x minus mu squared being greater than epsilon squared, the probability of that is the same as the probability of the absolute value of x minus mu being greater than epsilon. And a second thing that we can use is that the term on the right-hand side, so this expected value of x minus mu squared, it's the definition of the variance. So if we do this, if we rewrite using these two observations, then we essentially get to Chebyshev's inequality, and specifically we have that the probability of the absolute value of x minus mu being greater than some epsilon is smaller than the variance of our random variable x divided by epsilon squared. All right, so now we have two things. We have Markov inequality, which we have generalized into Chebyshev's inequality. So let's see if we can continue generalizing these things that will hopefully bring us to something that will allow us to bound the deviation of the true risk from the empirical risk, which is what we were trying to do. So then we will need one more lemma, for which I'm not going to show the proof, but I'm just going to show the statement. So this is Hoeffding's lemma, which says that if I have some random variable with mean 0, so expected value of this random variable x is 0, and if this x is also bounded, so it lies between some lower bound a and some upper bound b, then basically for any t greater than 0, the following inequality holds. So I can say that the expected value of the exponent of t times x is bounded from above by the exponential of t squared b minus a squared divided by a constant 8, which arises if you do the proof of this lemma. How can this be useful? So why are we looking at Hoeffding's lemma all of a sudden? Well, remember that Markov's inequality, and specifically also Chebyshev's inequality, gave us something that on the right-hand side had an expected value. So Markov's inequality was this: the probability that x is greater than epsilon was bounded by the expected value divided by epsilon itself. So now suppose somehow I also want to keep bounding the right-hand side, so keep bounding this expected value, then potentially you can see that this Hoeffding's lemma might come in useful, because that's exactly what it gives. It gives us a bound on the expected value of the random variable, and specifically the expected value of the exponential of that random variable. So that's the relation between why we're suddenly looking into Hoeffding's lemma. All right. From Hoeffding's lemma, the next thing I'm going to need is Hoeffding's inequality, and this guy already brings us a lot closer to the final thing that we want to prove. So Hoeffding's inequality states the following. Suppose I have some random variables x1 up to x capital M, which are independent of each other, and each of those xi's takes value in some bounded range. So for each of the xi's, we can have some ai lower bound, bi upper bound. Then, for any epsilon greater than 0, and if I define the sum of those random variables as this m, which is just the sum of these xi's, then basically I can obtain the following two bounds, which essentially says that the probability that Sm minus the expected value of Sm is greater than epsilon is bounded from above by an exponential of minus 2 epsilon squared divided by the sum of bi minus ai squared. And this should already make you see how this is going to be used for our generalization error, since essentially if we choose this SM to be our empirical risk, because it's going to be the sum of xi's, where xi's are going to be our losses, then indeed the expected value of this SM will be our true risk, and then we can somehow obtain a bound on the deviation of our empirical risk from our true risk. Before we go on with that, I want to do a quick proof of this Hooftings inequality, which follows from a few steps using Hooftings' lemma, so the thing we saw in the previous slide. All right, so we start with Markov's inequality. We start with essentially this bound that we had on the probability of a random variable being greater or equal than some epsilon. We rewrite this in exponentials because we need the exponentials. And then we basically bound this using directly Markov's inequality. So this probability that the exponential of tx is greater than the exponential of some t that we can choose ourselves times epsilon. Markov's inequality is bounded by this e minus t epsilon times the expected value of that random variable exponential of t times x. All right, then we go to the next step. We can then say that the probability that Sm minus expected value of that Sm, where Sm was defined as the sum of the xi's, is greater or equal than some epsilon, is bounded by, directly from the above formulation of Markov's inequality, we get this guy over here. Again, just Markov's inequality applied to this particular random variable Sm minus expected value of Sm. All right, then the right-hand side of that inequality, this exponential, expected value exponential, we can rewrite it by the fact that each of the xi's, so each of the xi's in the sum for Sm is independent. So we can take out this product, we can take it outside of the expected value. Then we continue rewriting that part. So we continue rewriting this product of exponential times expected value of the exponential. And we will just bound it using Hooftings' lemma. So for Hooftings' lemma, we had something that bounded the expected value of the exponential of tx by this exponential t squared b minus a squared divided by 8. And we just directly plug this into our inequality. Almost there. Then we rewrite this right-hand side, so this product of these exponentials, where we used Hooftings' lemma to remove the expected values or to bound them. We rewrite it as the sum again, so we basically take that the exponential product is the exponential of sums. And then final step is that we had this choice of this variable t that we could choose ourselves. We just said t has to be greater than 0, but what exactly t is, up to us to say. And we say, okay, we choose it to be this thing over here, because this thing will minimize the upper bound. It makes our whole bound look a little bit nicer. And then we basically get to the final Hooftings inequality statement, which had on the right-hand side this exponential minus 2 epsilon squared divided by the sum of the difference of the ranges squared. And then finally we get to the final step, which is applying these concentration inequalities. And remember that our goal was to bound the distance between the empirical risk, so our hat f, which was defined by this 1 over n sum of our losses over the samples from our data, and the true risk r of f, which was the expected value over our whole data generating distribution of our losses. We want to do this, we want to bound their distance using Hooftings' inequality that we proved before. And I have here in the right-hand corner. So then the first step is to make clear what are going to be our xi's. our xi's are going to be our losses. And because we assume that each of the xi, yi's are iid, we can also say that each of those terms of our loss function, so our loss of fxi, yi, all of them will also be iid variables. So that's the first thing we need to clarify in order to see if we can indeed apply Hoeffding's lemma. Second step, for Hoeffding's lemma, we also needed each xi, so in our case each loss of xi, yi, it needed to be bounded. In general, loss functions are not necessarily bounded. If we take the mean squared error, it can become infinity. So we need to take a specific choice of the loss function. So for our loss function, we then choose this 0, 1 loss, which is 0 if f and y, if our prediction f of x is equal to the true label y, and 1 if it's not. So in this case, indeed, this our random variable L of fx and y becomes bounded between 0 and 1. And in particular, in the notation of Hoeffding's inequality, a is then 0 and b is 1. All right, so this makes 1 over n times this loss function be bounded between 0 and 1 divided by n. And hence, if we look at what was in Hoeffding's inequality on the right-hand side, we get that this summation of the different ranges squared becomes this n times 1 over n squared. These are our b minus a squared, which essentially becomes 1 divided by n. And then we're almost there. We can directly apply Hoeffding's inequality to Sm being our empirical risk and expected value of Sm being then our true risk. And then we get the following final statement, which says that if we just look at the first probability bound that we get, it says that the probability that the empirical risk minus the true risk is going to be greater than some epsilon is bounded from above by an exponential of minus 2 capital N times epsilon squared. So what does this say to us? It basically gives us back something that might be potentially expected, which is that if we increase our data set, so if we make our n, capital N, larger, then the distance between the probability that empirical risk and true risk are going to be far apart is going to decrease, because this right-hand side is going to become smaller and smaller as n becomes larger and larger. That's it. Thank you.